Okay, I'm hopefully live. I can see myself, so I'm going to get started. I'm planning to answer questions at the end of the talk, but I will keep sort of half an eye on the comments in case there's something that y'all need to pass on to me. So my name is Jim Jarvis, and the topic of my discussion is techniques for safely staging high power rockets. I have an agenda to pass along here in a little bit, but let me first just introduce myself. I got involved in model rocketry back in 1962, I think, and enjoyed that for a while. And then I got back into the hobby back in 2003. I did my L3 in 2007, and I've been a member of the Austin Area Rocketry Group since that time, and I've been a AAA TAP member since, I think, 2013. There's some things in rocketry that I enjoy. One is high altitude staged rockets, and I'll be talking about some of that in the presentation today. I also very much enjoy flying a vertical orientation system that I designed. I actually have a few of these systems for sale to experienced high power rocketeers. So if you're interested in one, I'm easy to find. I also spend a lot of time mentoring. This year, I probably bitten off a bit more than I can chew. I've got a couple of teams in the SLI competition, two teams that I'm mentoring for the spaceport competition, and I have 13 other projects, mostly two-stage projects that I'm reviewing for that competition. And then it won't be long before Tripoli starts showing up with the Class 3 safety reviews. So I'm going to have a busy next few months doing that. When I was back when I was doing model rockets back in the 60s, one of the things that I really liked was the two-stage rockets. And I started out, the one I had was a Black Widow from Centauri. And I still drool when I see that kit. That was sort of the start of it. And in the high power arena, I started out with a Quantum Leap and promptly shredded that after a few flights, and then rebuilt it a little bit differently than what the kit was. And I still have that rocket, and I enjoy flying that. And then I got involved in composite staging rockets, two stagers and also three stagers. Those are a lot of fun. More recently, I've gotten involved with two-stage research rockets. Boosters typically a P or a small Q, and the sustainer can be a no motor. And I'm hoping to launch one of those this year at Balls. I've spent a lot of time doing high altitude flights. I usually try to do one every year. If I look at the 100K attempts, I've tried to do that 10 times, and I've actually gotten there 5 times. Some of those flights are better than others, but at least I keep trying to get there. So I do have some experience with staging, and so I thought what I would do is pull together this presentation just to share some of the experience and opinions that I have on the topic. And I'll say right now, this is not intended to be a treatise of everything that can ever happen with stage rockets. It's mostly just things that I've learned and some things that I've done and how I've gone about doing it. And there are certainly a lot of things and techniques in high power staged rocketry that I haven't done. So don't take my presentation to mean this is the only way that it can be done, because that wouldn't be the case. So I'm going to start out with just sort of an overview of staging and some of the preferences that I have on that topic. And then I'll transition into some safety topics. And I think that it's fair to say that Staged rockets present some challenges from a safety perspective, and there's some things that you should do, even starting from H motor stage rockets on up. And so I'm going to go through some of those things. So the first thing I just want to talk about is the importance of simulations. They're always important in rocketry, but they're particularly important when you're talking about staged rockets. Really, a good simulation is essential. It's sort of the starting point for a staged flight. One of the things you can get from it is just what's the stability of the stack and the sustainer itself. And I often see people setting up these. Let me back up. I review a lot of student projects, and so I have opinions and lots of observations from what the students are doing. So that's sort of the basis for many of my comments. I'll often see a long, skinny two-stager set up with a stability margin of maybe around 1.5 or thereabout. And it's my opinion that the stability is really more a matter of a percentage of the height. And so you might be looking at something like 2 to 3 calibers for the stack, which you wouldn't necessarily design for a single stage rocket, but for a two-stage project, that's sort of the target that you're looking for. And the other thing that's important is if you're doing a project where the sustainer velocity is going to be above Mach 1, you kind of want to design for greater than 2 calibers of stability, basically all the way through the flight. And that's a recommendation from Chuck Rogers, and I trust a lot of the stuff that Chuck says. A good target for initial acceleration is around 10 Gs. You want to get the stage rockets moving fairly quickly, and you don't want to be underpowered because you don't want to weathercock too much, because then that's going to adversely affect the remainder of the flight. Then you can look at the simulation to help you with the timing of the flight, and this is important. Where is it that you're going to fire separation charges if you're using them? How much coast time do you want? When do you want to ignite the upper stage? And so that can come from the simulation, and the results from that then can go into the development of the sustainer motor inhibition approach. How are you going to program the altimeters and the flight computers so that you don't get a flight where the motor lights when you maybe really didn't want it to do that? You can also look at the effect of the tilt angle on dispersion. I see a lot of student projects where they'll say, yeah, we're going to 30,000 feet and we're going to use a 30-degree tilt lockout. And you just sort of ask them, why don't you go through a simulation where you're at 30 degrees when you light the sustainer, and then look at your horizontal velocity and how far away you land, and then come back and tell me that you really want the motor to light, if indeed that's the angle that you're at. But you can get that information from a simulation. And you can also look at drag separation. That's always a topic. Should I rely on drag separation, or should I separate the stages with a separation charge? So to look at this, what I decided to do is just to set up let's just start setting up a flight, and then do a simulation and see what does the simulation tell us about the design of the flight that we're using. So I set one up to go with the M2245 as a booster to an L995, and that might be maybe a typical configuration for a student project going to 30,000 feet. And let's say we want to use a separation charge 2 seconds after burnout, and then maybe light the sustainer motor 2 seconds after that. And so we can set that up and then look at what the results are of the simulation. And so this is a simulation from RAS Aero, but you can get basically the same information from the other simulation products. So here we have velocity and acceleration and stability margin. So let's look at each of those first. Here's velocity. So this is what we got for our flight. And we can see that that booster motor is going to take us up to about 1,250 feet per second. And then over the coast period, it's going to slow down to maybe 850 feet per second. So we're kind of in the transonic range here for that coast and for the separation and then for the lighting of the sustainer. And you can probably do that, but it might be an idea to at least look at options where maybe maybe you use a smaller booster motor and you stay below the transonic, and then you use a larger sustainer motor to get to your ultimate altitude. Or you can arrange to fly above Mach 1 and stage above Mach 1 also. So here's where you might want to reconsider the plan and maybe look for some alternatives. And so here's the acceleration plot. And so you can look at the initial acceleration off the rail, and you can see that we're at roughly about 10 Gs here. So the motor looks fine. But then you can see as the motor tails off, here's where we reach 0 Gs. So that's where burnout would be detected. But you can tell there's still motor thrust being produced here. And in this case, for this particular motor, the thrust is produced for about a full second after an altimeter might tell you that you're at burnout. So you don't want to be firing the separation charge immediately after burnout is detected. You want to provide some time in there for the motor to be fully burned out, and particularly if you have a research motor and maybe the burnout maybe isn't as well characterized as a commercial motor. But you need to allow it enough time, because if you do the separation before the motor thrust is ended, you'll have generally speaking, a bad outcome. And the other thing you can look at on the acceleration plot is you can look at the point where you do the stage separation. Now, if you were planning on drag separation, you might separate the stages immediately when burnout occurs. But you can tell the simulation program to hold off on that separation for a couple seconds, and then you can look and see what happens to the acceleration right at the point where you stage separate. And so here's some examples. Here's a simulation with a heavy sustainer, and so you can see the deceleration of the rocket once the sustainer is separated is less than before the sustainer is separated. So in this particular case, it's evident that the sustainer is going to want to drag separate, because the resulting configuration has less drag than if the stages are together. And similarly, if you have a heavy sustainer, but maybe a heavy booster as well, maybe there's not much of a change there. But if you have a light sustainer on top of a heavy booster, you can see there's actually more drag after separation occurs. And so you can imagine if you take an Estes Alpha and put it on top of a Q motor, that the model rocket is never going to want to separate from that booster. So, this is just sort of an example of how you can see that from the acceleration profile. Now, this is not an exact calculation, because it's not including maybe something, drag separation of the sustainer at the moment that separation occurs, but it can at least give you an indication for a rocket as to whether or not that is likely to drag separate or not. So here's the stability margin, and we start out on this particular rocket at around 3, so that's good. And you'll notice it's very typical that as the booster motor burns out, that the rocket goes very overstable as after burnout, but before separation occurs. And it's hard to figure out how to avoid that, but a good practice is to try to separate the stages as soon as you can, bearing in mind that you need to wait until after burnout has occurred. And now here's the stability margin for the sustainer. And I know the numbers will be hard to read, but this is a little less than 2. So the recommendation is to stay above 2 calibers if you're above Mach. And so in this case, you might say, well, maybe I should increase the fin size on the sustainer so that I stay above stability calibers of 2, and then you might need to increase the booster a little bit to get back to a starting stabilization value of 3. So those are some things you can get off of the simulation, and there's a lot more, but those are the basic things that I would just recommend that you can look at just to get some insight into setting up a staged flight and some of the common problems to kind of avoid. And so now I'd like to talk about interstage couplers and a little bit about airframe design. Interstage couplers are really important because they need to be strong. They're handling a pretty good bending moment. They typically, or there may not be a lot of, I'll just say things that would strengthen the tubing right at the point where the rockets are together, and it's intended to come apart, so it's not a tight coupling as well. So interstage couplers need to be strong. I see a lot of two-stage projects where it'll be set up. So just as an example, maybe the interstage coupler is set up with slots for the fins to slide down into, and it looks really cool, but compromising the strength of the interstage coupler in that way is just not really a very good idea. You need to focus on what is typically a common failure for two stages, and that is basically a rocket will fold because the interstage coupler just isn't strong enough. Interstage couplers also need to deal with the wiring for the igniter and the separation charge if we're using one. You have to think about protecting the booster recovery equipment from the separation charge, or from the motor ignition, or from just the airstream, so that you don't inadvertently have recovery stuff coming out before you want to. They should be aerodynamic if you can, and it's perfectly fine to have electronics integrated into the interstage coupler in some way. So some of the different interstage couplers that I've used, I'm just going to talk about a few of them. One is the switch band method, which you typically would use on a non-minimum diameter rocket, and then something I'm going to call the motor mount method. And most of the time, this is something that you would use where you've got a increase in the size for the booster, and so it's difficult to use other techniques, but you can use something that basically is a designed, it looks like a motor mount as your interstage coupler. And then the last I'll call the motor tube method is just for a minimum diameter staging. And there's a lot of other techniques that I haven't used, and I think some of them are better than others. But again, I think the golden rule is to try to make them as strong as you can. So I'm just going to talk a little bit about each of these designs. So this is what I would call a switch band method. And just to get oriented, the sustainer is here on the left, and the green fins are on there. And then the interstage coupler itself is the pieces that are in red. And then the booster airframe is the blue sections that start here. So you might have recovery equipment, parachutes, and so forth in the right-hand part of the rocket. And so in the switch band design, typically it's designed so that the interstage coupler slides up inside the sustainer. And so you might have other stuff at that location. For example, you might have a conduit coming down into that location for your wiring. You might leave a cavity here for the separation charge and for the wiring that goes into the motor. And then you might have a recovery hardpoint on the interstage coupler. And then after the stages separate, basically the interstage coupler is going to serve as the nose cone for the booster. And one of the things that is important for these designs is that you shear pin that interstage coupler into the booster, but don't shear pin it into the sustainer. If the sustainer drifts apart due to drag separation, that's fine, but you want the interstage coupler to stay with the booster. I will confess to one flight where I didn't do this, and instead of the rocket separating at this point, the interstage coupler stayed with the rocket and separated at this point. And the flight wasn't a disaster, but it was pretty obvious there was something that was not right in the way that it ran. So you want to shear pin it to the booster. So here's an example or two of switch band design that I have on a rocket, and it's pretty simple, just a section of airframe and around the coupler tube. And one thing I didn't mention is that in this particular case, the thrust is transferred from the booster tube to the switch band section and then to the bottom of the airframe. So you want to make sure that those things fit well, for one thing, so that thrust transfer takes place smoothly. And then here's the bottom of that same rocket, and you can see that I have a conduit in there for the wires to come down. Here's just an example of a setup for a flight. And this is probably a good point just to mention that I don't like to see a whole lot of wires piled up down here. I like to see them come out of the conduit or from wherever and go directly into the back of the motor, and that there's not a whole lot of slack going on at that point, because those wires are subject to the separation charge if you use one, and to the wind once the rocket separates, and so you don't want to have a lot of excess wire dangling at that point. So here's another switch band coupler, and in this case I've got some recovery electronics that fit into the lower portion of the interstage coupler. And in this particular rocket, it was set up for an apogee deployment of the booster for this rocket. I've had ones where the electronics at that location were used to do the separation charge. So the second version of an interstage coupler is just what I'll call a motor mount method. And this method, instead of using a tube that goes up into the sustainer airframe, it's basically using the motor tubing that's coming down from the sustainer, and that's housed inside what is essentially a motor tube with centering rings, so it looks a lot like a motor mount, and needs to be designed with similar strength in mind, since that's going to handle the bending moment of the stages. And typically this design is something that you use when there's an expansion to a larger booster. Other aspects of it are similar to the switch band method. Again, you want to shear pin it to the booster tubing so that it doesn't come off. And you'll have the recovery hard point down there as well, because it's going to serve as the nose cone for the booster after separation has occurred. And here's just a couple examples of that type of interstage coupler that I've built. One of the things that you have to accomplish with this sort of an approach is that your wiring, if you've got, I don't know, my cursor's not behaving, but in this case, I'm bringing down wiring down the side of the motor using something called gecko cable, or tapper wire, it's sometimes called. And so that's going to fit into this motor tube that's in here. And I'll sometimes do this so that I have a little bit of a recess inside this tube to accommodate for that wiring. And if you do that, you need to be careful, because you don't want to have the motor, the sustainer motor, rotate within that interstage coupler, or you might jam the two things together if you've arranged for a fit that uses a gouged out section for the wiring, I guess would be one way to put it. So it's kind of good to key those stages together. And this is another interstage coupler of a similar design, and you can see I've got a lot of centering rings there for the motor mount. And then one thing you can see on this picture is that you can see the key in the airframe here that matches up with the key and the sustainer so that the sections don't turn against each other. And here's one more, same thing. Here basically are the rings that the motor is going to sit on, and I have a little gap in there, which is going to accommodate the wires coming down from above. And in that particular interstage coupler, I also had some electronics in there, and in particular, this was for the separation charge in this case. So the last one I'm going to talk about is the minimum diameter, and in this one, again, the motor is the thing that actually constitutes the interstage coupler. But here, there's something that basically I call a minimum diameter cap. That's the device that's in red, and that'll typically sit on a ring that's glued inside the top of the booster tube. And then the ring sits on that, and then the motor sits on the ring. And this is a surprisingly important device because it needs to be designed so that there's a little bit of room for the separation charge, and you have to be able to bring the wiring into it. And it's also important, since this is going to be your nose cone, that when time comes to separate separate this part and put out a chute, this has to be able to come out of the tube. So another way to say that is that the red cap can't jam within the airframe in any orientation. It has to be able to rotate freely no matter what orientation that it's in. So just kind of summarizing those things, that minimum diameter cap serves as the nose cone, and it's going to protect the recovery equipment from the separation charge and also from the airstream after separation occurs. It may or may not provide support for the sustainer, that is the thrust transfer, but it has to be designed so that there's a pathway for the igniter wiring. It has to have an area for the separation charge. It's got to be able to freely move out of the airframe for recovery. And as well know that oftentimes it's the weight of the nose cone that pulls out the chute and not black powder going off. So you can choose to weight these caps so that they'll more effectively pull the chute out when the time comes. These also need to be shear pinned to the airframe. So here's a few pictures. I have a lot of these, and I sort of conclude from that it works, but there aren't a whole lot of alternatives for how you want to do this if you're doing a minimum diameter stage project. So you can see this particular one, you can see the cavity for the separation charge, and in the lower one here, there's some keys in there that fit inside of a Cicerone motor closure. And in the upper right, there's a hunk of lead on the bottom of that particular coupler, or that particular cap, to increase the weight so that it'll help pull the chute out. A little bit on airframe design for stage rockets. One of the things I learned early on is that I needed to build stronger for staged rockets. I went through a phase where I was flying rockets up to 50, 60,000 feet in that range, and I kept having failures. And a lot of times you really can't tell what the cause of the failure is, because basically, the fins come off and the tubes break, and it's hard to forensically tell what happened. But one of the things I did was just start to build those rockets stronger. And then all of a sudden I started having more success. So one of the things I did in the tubes that I rolled for rockets was I just made them a little bit thicker. Another thing I did, I call it Jim's rocket rule of thumb #1. And that is if you want to keep airframe tubes from failing, whether they're around the fins or whether in couplers or whatever, the idea is to keep them round. It's when tubes start deforming and they're not round anymore, that's when the tubes fail or the coupler fails or the fins come off. So a good design practice is to try to figure out how to keep the tubes round. When possible, you can use motors as the interstage coupler. They're going to be stronger than most airframe materials that you might otherwise use. A good thing to do on stage rockets is to minimize tube breaks. I have a student project that I'm reviewing, and it's a 24-foot tall rocket. And they have 5 switch bands in the rocket for various altimeter locations. So there's easily a dozen or more tube breaks through there. So I'm kind of afraid that that's going to go up like a wet noodle. And you just encourage them to maybe take some of those tube breaks out, because you have 2 tube breaks with every switch band coupler, and it's a good idea to get rid of those. I also think fit and finish is important for 2-stage rockets. You want to have the tubes be square, and you want to have them fit well so that you don't have a lot of wobble in the sections. And then the last bullet I have on there is just getting back to keying the airframe sections so that you don't necessarily, if it's a problem for the stages to turn against each other, you want to have the airframes keyed so that those sections won't turn. And I'll say for various reasons, I don't have any rockets that don't have airframe keys. Almost without exception, I have the tubes oriented the way I want them. And it also makes putting in the shear pins easier. I don't have to line them up. I just put in the sections together around the keys and then pop in the shear pins without having to do any more work to get them lined up. So here's just a couple examples on strengthening the tubes for a switch band type design. I might line them with carbon or fiberglass or something like that. And then for couplers, you might have a bulkhead on a coupler, and you might have a U-bolt included in that. I make my rockets generally with zipperless couplers, and within those couplers, I'll add extra bulkheads. Not only do they help secure the U-bolt if you're using that, but they help keep the tube round at that point, which helps keep the tube from failing. And I've also found if you have 2 or 3 bulkheads in a coupler above the motor, you can survive a motorcado. Generally, the forward closure won't have quite enough energy to get through multiple bulkheads, and so you can save the upper part of your rocket if you have several bulkheads in there. Another technique that I use to eliminate tube breaks is I'll take an altimeter bay and I'll just arrange for it to sit within a longer tube and no tube breaks. And so the altimeter bay will just slide in and get pinned in the airframe at the right location, and you have access to the screws, but there's no tube break there. And so you can eliminate a lot of tube breaks with that approach. I like my couplers to fit. And I see a lot of people that wrap tape around radially around the couplers to snug them up. And I'll just share the technique I use, as mundane as it is. But I'll start out, I'll put a piece of tape vertically on the coupler, maybe at 4 locations around the perimeter of the coupler, and then I'll test that fit. And if that's not enough, then I'll add a piece of tape over the top of the first piece of tape, but it'll go a little higher up on the left there than the first piece of tape. So that makes it easy to slide the airframe on without ripping off the tape sections. once the final fit gets fairly snug. And if I need a third piece, I'll just do the same thing. It'll just go up just a little bit higher than the second piece. And so that's how I'll do it. And I generally have airframes that fit pretty well and separate pretty well. So I'd recommend that technique. I mentioned keys as something that I use. And here's an example of one. So I've got an airframe on the left and I've got a coupler in red on the right. And so the way I'll make a key is I'll just take a Dremel and I'll sand out a half moon shaped opening on the tube. And then I'll cover that area of that airframe with a release liquid of some sort. And then I'll put the airframe sections together and fill the little cavity over the coupler with epoxy. So I'll get a half moon shaped matching section that goes into the upper section. And then because I've got a release on there, I can separate those tubes and now I have a key. And I usually put 2 of these on any given joint of the rocket. I don't put them at 180, I put them maybe at 170 or something like that. And that's just so I can easily tell what the orientation is. And then, like I said, once you do this, now you'll find all the shear pin holes work. And if you're doing a 2-stage rocket and you've got, maybe 30 shear pins on that rocket, this can really help accelerate the process of getting it set up and launched. So the next thing I'm going to talk about is lighting the sustainer motor. The idea is you want to get the motor lit, and I see so many projects. I would say kind of an overall average. If I had to look at all of the different projects I've seen, I'm going to say probably the motor lights half the time. Sometimes it's not lighting because it shouldn't light, but a lot of times the igniter goes off and the motor just doesn't light. And so the golden rule here is don't allow if you're using a stick with the igniter on it, let's say, don't allow the firing of that to spit the igniter. When you light a motor on the ground and you've got a motor stick in there, you'll typically tie that off on the pad so that it won't get spit when it goes off. And you basically want to do the same thing on a stage rocket, because if you don't and it just spits the igniter, the motor oftentimes won't light. So one of the ways that I do that, if you look at the pictures, you can see there's some pieces of thread hanging out of the bottom of the nozzles. And I just use a couple of pieces of nylon string, although if you have very thin Kevlar string or Nomex, you can use that as well. But basically what I do is I'll put the motor stick in and then I'll wrap the string around the stick and hit it with a couple of drops of CA glue. And that way it'll hold the stick in the motor just long enough so that the motor will light. So don't count on the cap holding the igniter in place, because when the igniter goes off, it'll just blow the cap off and the stick will go with it. So you got to do something to positively hold the igniter in the rocket. Here's another technique that I've used, and here the idea is to hold the stick in maybe with a couple pieces of electrical tape, but you set it up so that the amount of the nozzle that you're blocking with the tape is not all that large. And then you can cover up the rest of the nozzle either with more electrical tape or with a cap. And then when the igniter goes off, it might blow the cap off, but it won't blow the stick out. So I've used a lot of different techniques for getting motors to light. I guess there's several schools of thought about how to do this. One is to go with sort of an instant on approach, where you provide enough energy and maybe a burst disk to try to get instant on for the motor. And that's kind of hard for amateurs to do sometimes. So a strategy that I kind of like is just to provide some fire for a longer period of time than just, maybe just the instantaneous motor igniter that often comes with the motors. So I'm not sure how many of these techniques are NAR friendly, but one of the techniques that I particularly like that I'll share is I'll take a forward closure and I'll drill a hole in that closure, or I'll pot it with glue and then drill a hole, and maybe it's a 1/2 inch diameter and maybe 1 inch deep, and I'll pot in that maybe 3, 4, or 5 grams of Magnolite. This movie will probably not work, but I'm going to go ahead and turn it on anyway to see if you can see it. But the objective is to get maybe 3 or 4 seconds worth of fire coming out of that potted Magnolite so that it lights the motor. Another thing that needs to get done at the bottom of the motor is to protect the wiring from the separation charge. And so I'll almost always put a cap on the nozzle or on the back of the motor or something so that at least part of the wiring is protected and the core of the motor doesn't get pressurized when the separation charge goes off. And the way that you need to do this will depend upon what what it is that's at the back of the motor. But I've invented all sorts of different little jigs and pieces and parts and so forth to basically cover off the nozzle. So it just depends what's there as to what you need to do to protect it. So as far as wiring to the igniter and to the separation charge, I always light motors from above. I don't like to light them from below because I want to have the sustainer separated from the booster before the motor gets lit. So the typical approach that I use, which I'm sure will horrify some, is I run the wires from the sort of a conventional altimeter bay down through the drogue bay and past the drogue and then down to the top of the motor. And I'll leave some extra room there so that the stages can separate and won't get constrained by that wire. But I've never had any tangling occur as a result of having done that. So I've also used for minimum diameter the Gecko wire and the Tapper wire. I have used head-end ignition, but I'll just say I only use head-end ignition when I have no other choice. I'll always try to come in the motor from the bottom if possible and use head end if I can't do anything else. One of my favorite ways to make brake wires, since there has to be a brake wire in that configuration, is to use these Dean's plugs. And the reason I like them is because I can file off the little prongs to where I get just the separation force that I want for the brake wires. And these don't have to be loose or anything, but when they're brand new, they're kind of tight. So I like to kind of adjust them so that they'll separate at just the resistance that I want. Talk a little bit about sustainer inhibition on the ground. And this gets into the second part of the presentation, some of the safety topics. It's a bad day when the motor light's on the ground, so you want to make sure that doesn't happen. My opinion is that basically there needs to be a switch between the altimeter and the igniter for any staged rocket that has high power motors. This can be a simple disconnect for the circuit down to the igniter, or there can be a disconnect shunt combo of some sort, but there needs to be a switch there. I'm also an advocate of what I call an all-up test, and this is a test that's done just before you launch the rocket out at the pad, and I'll talk a little bit more about that. I also see almost every student project that I get is using 2 altimeters and 2 igniters for the staging. And I generally say you can do that if you want, but my recommendation is that you just use 1 altimeter and try to do that safely, because it's hard enough to do it with 1 altimeter, and you just more than double the complexity of it if you use more than one altimeter for that function. You can use a high current igniter if the altimeter allows. Unfortunately, many of the common altimeters for staging don't really allow high current igniters. Another thing you can use is a Wi-Fi switch, and the Wi-Fi switch lets you basically turn on the staging electronics when you're not on the ladder, and it's important to be able to do that if you can as a safety measure. Then the last thing I'll add is when you're doing a stage rocket, sometimes they get larger and you've got a pad crew. And one of the things I just recommend to people is consider your pad crew in the process of setting up the rocket. I typically try to go through some kind of a tailgate to tell people, here are the things I'm concerned about as I set this up. The rail when we do this, and the igniter when we do that, and here's the things that concern me, and then try to have the minimum number of people present for any given operation as you go through the setup. So I see I'm running a little bit later than I had intended, so I'm probably going to skip through the next few sections fairly quickly. I got some slides in here on using switches, and you can go back and read them. One of the areas that if you're using two switches that's important is to design the circuit for the shunt. There's some ways that are better than others, and one of the things that I've done a lot over the years is I started incorporating resistors into these circuits. So if I'm using a shunt, I want to minimize the total amount of current going to the igniter shunt combination, as that will decrease the amount of current going to the igniter in the case that the altimeter inadvertently fails. So if you were to look in any of my altimeter bays, you would find resistors present there for that purpose. The all-up test is something that I just recommend people do for staged flights, and the objective of an all-up test is basically to turn everything on, and including the GPS, everything that is an electronic device in the rocket, and do that before you you want to do it in the same configuration as you're going to fly, and you want to do it with the igniter outside of the motor. And so you pass the test if you turn everything on just as you're going to do later, and the igniter doesn't fire. And it's sort of your last line of defense, because what you're going to do is you're going to turn off the electronics, load it on the pad, and then reproduce the procedure that you just did, and then fly the rocket. So the closer you can simulate that all-up test to what you'll do when the rocket is on the pad, the better. And I actually do this. I don't just recommend it, I actually do it. And in the upper left is a little device that I made so that I can set a rocket vertical on that, and I'm not going to screw up the wiring down below the rocket. So we'll set it in there with the igniter out of the rocket and turn everything on in that vertical configuration. And then if it works, turn everything off, pack it up, and load it on the rail. Here's one little trick. I mentioned I don't like to have a lot of excess wire at the bottom of the igniter. So what I'll do in the first picture is I'll just have the wires coming down from above, and then they'll go right onto the rocket stick that's holding the igniter on there. But the trick is only tape the wire to that stick halfway down. And if you do that, you'll find out that you can pull it in and out of the motor without having to have any excess slack in the wire at the bottom of the motor. And it's sort of hard to visualize it, but when you try it, by golly, you can pull the igniter out, and that lets you do the all-up test by pulling the igniter out. I've got a lot of rockets that have Wi-Fi switches in them. One of the things that I don't like about staging is being up on a ladder when you're turning things on. I can say I've had one close call with that, where literally a jiggling of the rocket could have caused the sustainer motor to go, and that's enough to get your attention. And I've certainly seen other people have problems with motors lighting on the pad. So it's a real problem, or real issue. Wi-Fi switches can help you solve it. Wi-Fi switches aren't really switches. What they are is switchable batteries. So you can turn on the Wi-Fi switch itself on the ground, and then once the rocket is elevated, then you can turn on the Wi-Fi switch, which turns on the power to the altimeter. Now, because you're depending upon turning the switch on and off with a Wi-Fi signal, sometimes you might not be able to make that signal work. And so the Wi-Fi switch itself has to have an external switch that you can use to turn the Wi-Fi switch off in the event that you need to stand down and you can't get the Wi-Fi signal. And one thing I learned with Wi-Fi switches, obviously you got a problem if you're using carbon fiber airframes. But a good friend of mine named Ron Parsons knows a lot about altimeters or a lot about antennas and how to make radio signals work. And he showed me that I could use something called a slot antenna. And if I just put that in the side of the airframe, that would let the Wi-Fi signal in and out of the airframe. So if you looked at my rockets, you find a number of them anyway that have that sort of slot in them, and it's designed for using Wi-Fi switches in combination with carbon fiber airframes. Another thing that I recommend people think about is that switch that goes to the igniter. Try to figure out how to do that so that you can do that from the ground and not from the ladder. And there's a whole lot of ways to do it. You can use pull pins and so forth. Here's one that I used where the shunt is that magnet. So I'll stick that magnet on those screws, and that's the shunt, and then I'll have a string tied to the magnet. I can just pull it off when I'm standing on the ground, and it's the last thing I'll pull off before launching the rocket. Lifting the rocket is something that I really stresses me out, because I hate having people do the Iwo Jima lift on a heavy rocket. Pads corrode and fail, buttons can break, and I just don't like people to be around the rocket when I'm going through that lift. And I'm not sure if this will work. I'm thinking it's not going to work. But basically, I have a winch that lifts the rocket, and there's nobody around it when the rocket is being lifted. And so the next topic is just inhibiting the sustainer in the air. You want to inhibit it on the ground so it doesn't go off when you're nearby it. But you also want to inhibit it in the air in case the flight is not going well. The last thing you want is a sustainer pointed toward the ground and it lights and the rocket starts coming back toward you, or it goes off at some very low angle, and lands off property somewhere. So the two things that you can do to prevent that are to use a tilt on the altimeter, and even more importantly is an altitude check with the altimeter to inhibit sustainer ignition. In the case of tilt, you want to make sure that it actually is tilt. There are altimeters that use inertial versus barometric altitude for a sort of a pseudo tilt check, but there are altimeters out there now, common altimeters that will use tilt, and you can use those to inhibit the motor. Don't use a simple timer. If you use a simple timer, you don't have either a tilt check or an altitude check, and the motor's going to light no matter what happens in the flight, and you don't want to fly high power rockets that way. Another thing to just consider is to use good judgment when you set the tilt threshold. Use your simulation to figure out if you really want it to light, if you are at the extreme margin of the setting that you're using. So I probably don't have time to go over the details of an altitude check, but basically it'll be here on this slide and you can go back and look at them. You rely heavily on the simulation in order to come up with the approach. And then you have to combine that altitude check with the way that the altimeter is designed to use that altitude check. And it's different. Altus Metrum and Blue Ravens use a different strategy for altitude checks than older Ravens. One thing I will point out here on this slide is that in my opinion, the range in which the igniter should light should be very narrow. I set them up so there's maybe a couple seconds where, if you're at the altitude that you need within that time window, it'll go. And if you're not at that altitude, it will not go. And furthermore, it won't go after that. You have basically you close the window on the time that it can light. When I see two stages set up to light anywhere between 3 seconds and 12 seconds, my eyes kind of cross over. There's a couple of recovery issues that are real important for staging. One is just to remember that if the motor in the sustainer doesn't light, the sustainer is going to be a whole lot heavier. Some of the high altitude flights that I do, the propellant is more than half the weight of the rocket. And you have to design the recovery system to deal with the extra weight that might be there, because it commonly happens that the sustainer motor doesn't light and you can't have it coming down at an excessive speed. The other thing, I think a lot of the things that are difficult about staging is just what happens when things don't go right. And one thing, don't over constrain separation charges. You want separation charges to go off before your recovery system deploys. So don't over constrain them with tilt control and altitude checks and so forth. Just let them fire when they're supposed to, so that the parts will be apart even if the flight isn't perfect. Last comment I'm going to make is just on checklists. I don't use a lot of checklists on single stage rockets. When I get into these multi-stage rockets, I have very detailed checklists. For some of the flights I've used, I had a 7-page checklist that basically lists every step I'm going to do. Right from the, literally from the start to the end. And when I'm going through and doing the prep, I don't think about it. I just execute the checklist. I remember I was at a launch once, and Stu Barrett and I were flying a rocket, and we were going through this. And at one point in time, Stu says, can I do this? And I just locked up, because he's asking me to do something that's not on that we haven't got there on the checklist yet. And I literally can't answer the question at that point, because I want to follow the checklist. And so I think they're important, and I would advise that they be just literally as detailed as you need to, so that you know exactly what step you're going to do sequentially. And that's all I have. So I'm going to go back up, and I'm going to look at questions. I don't see a whole lot of them. Wait a minute, I see some Q&A. I'm going to have to go to those. Yeah, James, there's a reason you haven't been on a pad crew. Yeah, Chris, the Wi-Fi switches are great. I think I've had student projects that have had 4 Wi-Fi switches in them, and the setup of them and the arming of them just goes almost always very smoothly. Okay, can you explain that external shunt you showed? I'm not sure what that refers to. The only shunt I showed that was external, I think, was the magnet, and it just literally shorts out the igniter leads. It's sort of like twisting the wires on the igniter, and it just, I've got some copper wrapped around the perimeter of the magnet, and so it's a nice low resistance shunt that I can put on there. I don't think the slide set is available. I probably could figure out how to do that, but it'll show up when you review the video for sure. The length of the Wi-Fi slot, yes, there is a specific length, and I don't remember it right off the top of my head, but basically it's like a quarter wavelength. It's like 6 centimeters or something like that for the frequency that of the device that I'm using. I do not have a list of preferred switches or that sort of thing. I try to mention them in the videos, this video, and in the 2021 video. I listed some preferences as well, but I don't have a list per se. High current igniters, I'm really not sure. I know that the Altus Metrum stuff will basically, it has a circuit in there that's designed to limit the current in the event that the current draw is so large that it is going to brown out the electronics in the altimeter. And I believe the Blue Raven is limited to something like 4 amps. Beyond that, I'm really not sure, but it's just something that you know, it won't necessarily always be listed in the specifications for the altimeter. You may have to go ahead and contact the manufacturer to find out what it actually does. Thrust structure for minimum diameter usually is just airframe to airframe. Very rarely I'll have a rocket which is not airframe to airframe, and then I'll have to rely on some other means, but I'll bet probably 9 out of 10 times it's airframe to airframe. I've got a test rocket for my stabilization system that is fairly complicated on the interstage coupler, and that one's not airframe to airframe. 3D printed coupling hardware, an adequate manufacturing method. Well, I'm not exactly sure what that would be. I would say that you know, as I said earlier, the recommendation is just simply to design the interstage coupler as strong as you can. I have no problem with something that is a shell, which then gets reinforced in some manner. You can do that. But what I particularly don't like is when the whole interstage coupler is 3D printed. I've not found one that I found to be very satisfactory there, and I don't like to see them when there's slats in them for the fins, because it just reduces the strength of the thing that probably needs to be the strongest place in the rocket. Favorite coupling method is just to use the motor tube if I can. It's the strongest part of the rocket, and you know, it generally will give you the most strength. Now, of course, it's got to be, you know, it can't have a thrust ring on it, or generally it can't have a thrust ring. I'll say sometimes I have a rocket with a thrust ring, and I'll put a airframe section up above that thrust ring, and then the whole thing will slide down into a booster tube that's a little bit oversized. So I have used motors that do have thrust rings, and that's how I'll do it. Why does the minimum diameter cap show pins when it needs to be ejected? I'm going to have to stop and think. You know, I came up with the reason a couple of days ago why that needs to be sure pinned in, and I'll be darned, I can't remember right at the moment why that is. But trust me when I say that there is a reason why that cap needs to be sure pinned in there. Simulation software, I use all of them. I've used RockSim over the years. I use RAS Aero. I use RockSim mainly for the stability, the static stability. And I use RAS Aero for the altitude and the aerodynamic characteristics. And I'm getting better using OpenRocket. I haven't used it a lot, but over the last year or so, I'm starting to get more familiar with it. Do simulations accurately predict drag separation? Well, the method that I talked about in the presentation will use the, you know, does give you a measure of the tendency of the rocket to drag separate. I will say it's only a tendency, because remember, as the rocket's flying along, it's seeing bending moments, it may be rotating, and so all of those things are going to tend to be less certain on whether or not it actually drag separates when the time comes or not. So with one exception, I don't rely on drag separation. I always have a stage separation charge. And I do have one rocket which is just so heavy on the sustainer, it almost, is unavoidable that it will drag separate. So I'm not using a separation charge for that, and indeed I can't for that design. But that's the only exception. Every other rocket I've ever flown, I've used a separation charge. And okay, one more question over here. Says igniter wire down the conduit from the sustainer. Do you do anything to break the wire to keep it from inhibiting the drogue coming out? My experience is that the wire breaks with the ejection charge, but I always worry about it. Well, I use the little pins. Typically what I'll do is most of my rockets will have a zipperless coupler. So I'll run a conduit from the zipperless coupler down into the motor area. And then right above the zipperless coupler, that's where I have the Dean's plugs fittings where the break will occur. And then coming from above, the wires will go down through the drogue bay, and they'll have a couple extra feet of slack, and they'll attach to the Dean's plugs there right on top of the zipperless coupler. And that probably is 90% of the ways that I do it. So I'm not seeing any other questions. So with that, I will wrap it up. If you run across any more questions that you have for a particular project, you're welcome to contact me. I'm pretty easy to find, and I'm happy to answer questions. So thanks everyone for attending, and enjoy the rest of the conference.